Hello everyone. In 3D virtual environments, having a map can be incredibly helpful. While maps are often crafted by talented artists, when procedurally generating a terrain, we require a different approach. The map has to be created programmatically. To do this for my procedurally generated smooth voxel terrain, I came up with two ideas. We could generate a height map texture based on the octree, which involves ray marching through its stored signed distance field. Alternatively, we could use the rasterization pipeline to capture a depth texture of the world from above. I chose the second option. It's simpler, highly customizable, and fast enough for real-time use. So what exactly is rasterization and how do we use it to render the map? Rasterization is the go-to technique for 3D rendering in computer graphics. In essence, it first transforms triangle meshes into so-called clip space. Then, it identifies the fragments or the pixels in a texture influenced by each triangle. Finally, those pixels are colored according to custom fragment shaders. Let's focus on transforming objects from the world into clip space. The view frustum is a region of space that is supposed to be rendered to the screen and extends from the near to the far plane. To enable rasterization, the frustum and objects within are transformed into a box based on camera settings. This transformation uses the model view projection matrix, which is a combination of three matrices. The first is the model matrix, and it describes the object's transformation in global space. The second is the view matrix, and it transforms objects from the world to camera space, where all vertices are defined relative to the camera. Finally, the projection matrix, which commonly comes in two flavors. Perspective projection mimics real-world vision, where closer objects appear larger, and orthographic projection, where objects stay the same size regardless of distance. During rasterization, each pixel's depth is calculated as a value from 0 to 1 between the near and far planes and written to a depth buffer. This helps in discarding pixels with greater depth than what's already drawn, allowing for order-independent rendering of opaque objects. Limited by the number of bits to represent this depth, an inverse relation to the Z position in clip space is used for better accuracy close to the camera. In orthographic projection, a linear depth mapping from the near to the far plane will do, as all objects appear equally far away. For our minimap, we need a global height value, not depth from the camera. Since orthographic projection is ideal for maps, we can easily convert from depth by undoing the linear mapping described before and subtracting it from the camera's height. Unfortunately, the default Godot engine does not allow you to just render the depth buffer to a texture, so we will have to create a shader that renders the opaque depth buffer to a transparent quad in front of a secondary viewport camera. But how do we display this height? Humans are not great at interpreting a linear color gradient, as you perceive luminance non-linearly. This is a problem for our map, as we want players to be able to make informed decisions about the height and gradient of the terrain. To solve this, Isoline maps have been used effectively for centuries. The idea is that we connect points of certain equal elevations with lines. I achieve this using a two-step process. First, we expand our shader to discretize the height into distinct color bands that each describe identical height ranges. I additionally chose to split the map into two regions based on height, namely water and land. Then, we add an edge detection post-processing stage to the map texture. While the canny edge detection algorithm is common and pretty good, I decided to simply color a pixel slightly darker if the pixel above or next to it is a different color. This results in very clean 1 pixel wide subtle edges, but it only works because we discretized the image earlier. Finally, I added some markers. In many multiplayer games, you have the option to ping a location, and most games with a minimap also include markers to help the player locate points of interest. We define markers at a chosen 3D world position. To render a marker on the map, we project it to the map's plane and scale its position to match the map's scale. Optionally, we clamp it to the edge of the map such that it's always visible. To render the map to the player's HUD UI is a little more involved. First, we project the point onto the screen using the player's camera's view and projection matrix. This works fine if the marker is in front of the camera, but not when it's behind. To ensure it stays visible around the screen boundaries, we can adjust its position using the direction to the screen edge. The map I presented today is relatively simple to implement and should work in any environment. Best of all, it is computable in real time, so it could easily be integrated into a game as a minimap, for instance. The only major downside is that the terrain needs to be meshed before rendering the map. For more information on the rasterization pipeline, please refer to the amazing OpenGL pages I've linked below.